Welcome back, focused learners. Man, I am absolutely thrilled to have you here for another explainer. Today, we're going to unlock one of the most brilliant, literally game-changing concepts in all of mathematics. And hey, don't worry, we are going to do this without any of that usual math anxiety. Actually, scratch that. I want you to completely forget about textbooks and messy formulas for a second. We're going to strip this whole thing down to its absolute most playful, basic foundation.
So imagine you're standing in front of a giant cookie factory. You dump a certain amount of flour in one end and boom, you get a certain amount of cookies out the other. Now ask yourself, if I put in just a tiny bit more flour, exactly how many more cookies do I get out? You know, that simple, intuitive question, how much does the output change when I tweak the input, is the grand secret of calculus. It's called the rate of change. But to really wrap our heads around how this invisible math governs the real world, we kind of need to take our theoretical cookie factory out onto the open road.
Okay, let's dive into this. Imagine you're riding a bicycle, right? Just cruising along at a flat 50 feet per second. Well, that's your speed. It's basically just asking, how fast am I moving right now? But what if you aren't just cruising? What if you start pedaling harder and harder? Suddenly, you're gaining, say, 5 feet of speed every single second. Now that is acceleration. The distinction here is super simple. Speed is how fast you're moving right now, but acceleration is how fast your speed is changing.
Let's ground this in some actual numbers. Think about a moving body where its position is dictated by the time cubed. That means its speed equation is 3 times time squared. And hey, don't sweat the letters, just look at the results with me here. At exactly 4 seconds, this body is moving at 48 feet per second. At 5 seconds, it's cruising at 75 feet per second. That is a total gain of 27 units of speed in just 1 single second. But here's the absolutely crucial part to understand. That speed didn't just magically jump from 48 to 75. It didn't teleport. It changed continuously over that entire second.
And because it changed continuously, saying the acceleration is exactly 27 isn't quite right for the precise moment of 4 seconds. So let's grab our mathematical magnifying glass and really zoom in on the data. If we check the tiny interval from 4 seconds to 4.1 seconds, the average acceleration is 24.3. Let's get even closer. From 4 to 4.01 seconds, it's 24.03. Even closer, from 4 to 4.001 seconds, 24.003. Do you see what's happening here? As that time interval gets microscopically smaller, as we mathematically shrink our window closer and closer to zero, we are zeroing in on a precise true value.
And there it is, the limit. At the exact moment of 4 seconds, the acceleration is exactly 24 feet per second, or 24 feet per second squared. Every single second, the speed is increasing by exactly 24 feet per second right at that specific instant.
Now, what's really interesting about this is how it reveals this unbreakable sequential family tree in the math. You see, position tells you, where am I? If you find the rate of change of that position, you get speed, which is how fast am I moving. And then if you find the rate of change of that speed, you get acceleration. How quickly is my speed changing? It's this perfect chain. Position leads to speed, which leads right to acceleration.
But here is where we make a massive shift in how we see the world. This math isn't just for mechanics or rocket scientists. The bigger, way more profound question is how quickly is any quantity changing? Whether we're talking about the growth of a bacterial colony, the crazy fluctuating price of a stock, or even just how fast your coffee is cooling down right now on your desk.
Picture this instead. A little stone drops into a completely quiet pond. Plop! It hits the water and perfect circular ripples spread outward. Or, imagine a circular balloon being inflated. As the radius of that ripple or that balloon grows, the area inside it grows too. We all know the classic formula. Area equals pi times the radius squared. But here's the catch. The area doesn't just grow at some steady, constant rate.
Let's look at the actual numbers for a second. When the radius is 3, the area is 9 pi. When the radius grows to 4, the area jumps to 16 pi. So the radius grew by 1 unit, but the area grew by 7 pi units. So does the area always change 7 pi times as fast as the radius? Absolutely not. Because the formula squares the radius, the amount of area added depends entirely on how big the circle already is. It's like a bigger circle adds way more area for the exact same tiny push in radius. So just like with our speeding car earlier, we got to zoom in again. And just like with the car, we shrink our window, push the radius just a tiny 0.1 units to 3.1, we get a rate of 6.1 pi. Make it 0.01 to 3.01, it's 6.01 pi. Make it 3.001, and we get 6.001 pi.
I mean, you can see the pattern, right? As our change gets infinitely small, the math steadily, beautifully approaches an exact number.
And that number is exactly 6 pi. In fact, if we derive the general formula for the change in area with respect to the radius, we get 2 times pi times the radius. So when the radius is exactly 3, we just plug that in. 2 times pi times 3 equals exactly 6 pi. It perfectly matches our zoomed-in table from before. At that exact moment, the area is growing at a rate of 6 pi square units for every single unit of radius change.
And this brilliantly illustrates what mathematicians call the chain rule. It's this incredibly powerful tool that lets us link multiple changing variables together, which, let's be real, is exactly how the real world operates. Because what if the radius itself is changing as time ticks by? Say the ripple's radius is growing by 2 feet every single second. How fast is the total area of the pond's surface expanding? Well, we mathematically link the growth of the area to the growth of the radius, and then the growth of the radius to the ticking clock.
We literally just multiply them together. We take our area rate of 6 pi, multiply it by our radius growth rate of 2 feet per second, and boom, we get exactly 12 pi square feet per second. That is the exact speed the area of the pond is expanding at that very instant. Pretty cool, right?
Let's take a step back and see how this builds into something truly incredible. This is the grand architecture of calculus. We looked at a moving body, where the rate of change of distance gave us speed. Then we looked at a pond, where the rate of change of the radius gave us the expanding area. Cars on a highway and ripples in a pond? They are completely different physical realities, yet they use the exact same mathematical logic. No way, right?
Which brings us to the big idea, the universal truth of calculus. Rate of change is simply the change in output divided by the change in input right as that change approaches zero. Whether it is flour turning into cookies, time translating into a rocket's acceleration, or a radius expanding into a balloon's area, it's universally about how much one thing changes when another thing changes. So all of this distills down to this single, empowering definition. A derivative tells us how quickly one thing is changing at one particular moment or point. That's it. That is the whole secret to calculus. It's not just a bunch of abstract equations, it is the fundamental language for describing a universe that is constantly in motion. So the next time you drop a stone in a pond or step on the gas pedal of a car, ask yourself what else in your life is changing. And if you could freeze time right now, how fast is it happening at this exact mathematical instant? Once you see the world through the lens of derivatives, honestly, the universe never looks quite the same. Thanks for exploring this with me today, and I'll catch you in the next explainer.